Welcome to The Explainer. Today, we are cracking open the essential toolkit that every single investor needs to really get a handle on risk and return. All right, let's jump right in. Take a look at these two funds, Fund A and Fund B. Now, on paper, they look like twins, right? Both have the exact same average return, 10%. But would you feel the same putting your money in both? I mean, look at Fund A. It's a pretty smooth ride. Fund B? Whoa, that's a total roller coaster. This is the perfect example of why just looking at the average, well, it doesn't tell you the whole story. And that right there, that is the million-dollar question, isn't it? If the average is the same, how do we spot the risk that's hiding just beneath the surface? So let's get into it. The first step is to really understand let's call it the true personality of an asset's returns. And we do that by looking at the shape of its distribution. Okay, and that brings us to our first cool tool, Skewness. In simple terms, Skewness just tells us if the distribution of returns is kind of lopsided. A positive skew, which is what we're looking at here, means you've got this long tail on the right side. And that can be a super important clue about the potential for some rare but really big gains. And here you can see exactly what that looks like in practice. It's pretty interesting, right? Notice how most of the returns are all bunched up over on the left, but then you see that long tail stretching way out to the right. What this is telling us, visually, is that there's a higher chance of small losses, but also a small chance of a huge gain. It's got more upside potential than the average would ever let on. All right, next up in our toolkit is kurtosis. So if Skewness was all about being lopsided, kurtosis is about two things: how peaked the distribution is and how thick its tails are. Now, high kurtosis, which gives us what we call fat tails, is absolutely crucial for understanding the risk of those crazy, extreme black swan events. And that goes for both the good and the bad. And boom, here's a perfect picture of a distribution with those fat tails. See how most of the returns are packed really tightly around the average? It's a sharp peak. But then look way out at the ends. There's a much higher chance than you'd normally expect of a massive swing, like way out at minus 20% or plus 20%. These are those rare but game-changing events that can make or break a portfolio, and kurtosis helps us spot that danger. So what's the big takeaway here? It's that by understanding the shape, using tools like Skewness and kurtosis, we're already building a much more sophisticated and frankly realistic picture of an investment's risk. But, portfolios aren't just about one asset sitting all by itself. The real magic, the whole point of diversification, is about how different assets play together. So let's try and see what that relationship looks like. Okay, so check this out. When we plot the returns of tech stocks against the broader S&P 500, a really clear pattern emerges. See how the dots form this tight group, all moving up and to the right? It basically means that when the S&P 500 does well, tech stocks tend to do well too. They're kind of moving in sync. But now, look what happens when we swap out tech for utility stocks. Whoa, totally different story, right? The relationship is way weaker, the points are just scattered all over the place like a random cloud, and this visual difference right here is the absolute key to diversification. You want to find assets that don't just move in lockstep with everything else. So our eyes can definitely see a relationship, or a lack of one, in those scatter plots. But as analysts, we can't just eyeball it. We need to be more precise. We need to put a number on it. The first stop on that journey is a metric called covariance. It gives us a raw number that tells us if two assets tend to move together. Positive number, they tend to move in the same direction. But there's a catch. The size of the number is really hard to interpret on its own because it's influenced by the volatility of the assets themselves. A big number doesn't automatically mean a strong relationship, which is not super helpful. So, to fix that little problem, we use the correlation coefficient. Just think of it as the cleaned up, easy-to-read version of covariance. It standardizes everything into this beautiful, clear, and simple range between -1 and +1. Suddenly, everything becomes instantly comparable. And this chart here just lays out that simple, powerful scale perfectly. A correlation of +1, that means two assets move in perfect lockstep. A -1 means they move in perfect opposition, which, by the way, is kind of the holy grail for diversification. And a 0, well, that just means there's no linear relationship between them at all. Okay, so we've got our nice, clean, precise number. We're done, right? Not so fast. Even with a number as great as the correlation coefficient, there is a massive, fundamental trap that we have to be so careful to avoid. And here it is. This might be one of the most important rules in all of statistics and finance, so burn it into your brain. Correlation does not imply causation. I'll say it again. Just because two things move together, it does not mean one is causing the other to happen. Yeah, sometimes correlations are just statistical ghosts. We call this spurious correlation. It could be totally random chance, or maybe there's some hidden third factor causing both things to move. I mean, a famous, kind of silly example is the strangely high correlation between liquor sales and atmospheric CO2 levels. Obviously, one isn't causing the other, right? To really, really hammer this point home, let's look at something called Anscombe's quartet. Check out these 4 different data sets. If you just look at the stats on paper, they seem identical. They have the exact same means and the exact same correlation coefficient of 0.816. But then you plot the data, and the whole story just blows up. The same exact statistics are describing 4 wildly different realities. The first one is a nice, clean linear relationship, just like you'd expect. The second is a perfect curve. And the other 2, they're totally distorted by one single massive outlier. This is the ultimate proof of why you can never, ever just rely on a single number. You have to see the bigger picture. You have to visualize it. And all of this leaves us with one last, really crucial thought. These statistical measures, they are incredibly powerful tools. But they're just that, tools. They only really work when you're willing to look beyond the surface, to actually visualize the data, and to understand the full story that the numbers are trying to tell you.